Hey everyone, welcome back to this course. In this video, I just want to go over the first module for EE 151. So here I'm on the Canvas page for section 5, and I've got the first module. It's on a course overview, Arduino and electronic devices. So here we've got a set of intro slides, which I'll open up in one tab, and we've also got the lab activity posted. As well as a place for me to capture points for the demo, and then a place for you to submit your lab notebook, which we'll get into, and then a place to take the quiz, much like the quiz in the course information module from last week. So let's just quickly go over these intro slides. We'll be going over them in more detail during the lab session, but here I just want to give you a high level overview of everything. Um, welcome to EE 151. This is the lab for Intro to Electrical Engineering. Here's a catalog description. My name's RJ. Here's some facts about me. Um, this is just a kind of like a cost breakdown for what it is for you, what it costs for you to be here, and kind of like motivation as to why you should really pay attention in class and try to take as much out of it as you can here. So we'll be going through a lot of material in this course. And honestly, it'll cover most of what you'll be learning over the course of 4 years, just at a really high level, and we'll be going through a lot really fast. So just try to pay attention, try to keep up. If at any point you feel a little bit underwater, please let me know, and we'll try to slow things down a little bit. We do have that flexibility in the material here because we are going fast, and understandably, if you need more time, then let me know. So you should already know this, but our course material will be hosted on Canvas. Um, we've already seen that. I've talked about the grade breakdown, and then this is just kind of a point on how the weeks will go. So there will be a pre-lab assignment and some kind of experiment or some class activity really, and then a quiz. The quizzes are meant to be kind of like a knowledge check, so they shouldn't be too stressful. And they're open note, so whatever resources you've put together, you're welcome to use. Just try not to give someone the answers to the questions. That's academic dishonesty. Um, so for the experiments, we'll be working in groups of 2 to 3 people, and you can assign yourself to a group on Canvas, or you can let me know what your group is and I'll put you in those groups. So let's just take a moment to look at what that looks like. So over here on the People tab, there's another tab here that says Lab Group, and you should be able to kind of like create a group, and then move yourself into the group, I believe. So if you have any trouble with that, let me know. The last 3 weeks we'll be mostly focusing on final project work, so kind of jumping on everything that we've learned and putting it all together into kind of like a final project that will be defined by your group and will be presented to all the groups. So this is just reiterating that point, that you'll be designing something and it should have fairly sophisticated hardware, software, and mechanical aspects to it. I mean, obviously, it's not the final product that you'll be putting into production, but I expect high quality in all of those regards at the very least. And then you'll have to write a report just gathering all of the information, design requirements, how your design works into written words, and then recording a video, kind of like to present your project so that everyone can view at their leisure. So now we're going to jump into talking about the Arduino. So here's the Elegoo kit that I keep bugging you guys to purchase. We'll be using this today as well as every week in this class, trying to look at all of the different components. And there are a lot of components in this thing, so we won't have time to get through all of them, but we'll try our best here. So, for those of you that are unfamiliar with Arduino, it's a hardware and software company. They're based in Italy. A lot of what they produce is open source, and it's just a great way to learn electrical engineering, right? Because we can look at the schematics, we can learn about microcontrollers, we can learn about digital, analog, everything, um, all in this little package that's relatively cheap. So it'll be a good resource for us. So the Arduino kit that I keep telling you guys to purchase has this Elegoo Mega R3 board. So that's shown at the bottom here. And it's an implementation of the Mega 2560 Rev 3 board by Arduino. And again, so things that Arduino produces is open source, so companies can kind of make their own copy and sell it on the marketplace there. So fortunately, even though we're using kind of a third-party development board, we're still able to use all of the tools that are available on the Arduino website. So just for example, there's a bunch of documentation on hardware, software, programming, which we'll be diving into a lot more. So here are just some of the hardware resources. We'll be talking about the pinout, data sheet, and schematics of this board, just to give you an idea of what those look like if you haven't seen any of them before. So here's the pinout. It's just a high level view of the board pins. It has a legend. You know, if you were to open up this page, there's a legend on the bottom of the page here telling you what each of the pins do kind of at a very high level. So for example, there are some ground pins on your Arduino, there are some power pins. And for the power pins, you can see there's 3.3 volts and 5 volts and some kind of VN. So all of these power ports are referenced to ground, right? You can't have voltage without there being, two different levels defined, right? So this is plus 5 volts with respect to ground. You can think of voltage kind of like a height almost. Um, there are some built-in LEDs on the board, and those are shown up at the top left here, and they're kind of traced out into the middle sections of the board. They're digital pins, analog pins, and we'll be digging through this a lot more. I'm not going to go through all of this right now. There are a couple more pages. But one thing to note that here is our microcontroller that's on the board, and we'll get into that a little bit more later as well. So the datasheet provides information, detailed information on the board. Right, so there's a list of features, which probably mean absolutely nothing to you at this point, but as you progress through your career, they might mean something, and we'll certainly try to pick up some of these terms as we go along through our course. Another really important thing within the data sheet is a set of electrical ratings for safe operation. And you'll actually get a chance to dig into those a little bit during the activity portion of this lab. Here's the schematic for the Arduino Mega 2560 Rev 3 boards. And it's a relatively short schematic, but I know for someone who hasn't seen a schematic before, I can see how this would be rather intimidating. So, as we progress through the course, we'll try to pick up on little bits and pieces of the schematic so at the end of the course, hopefully we have a good idea of how the Arduino works, right? These Arduino boards work internally rather than just kind of like as a plug and play device, because we want to dig deeper and have a better understanding. And so the last resource that I wanted to point out are these programming resources. And I know a lot of you don't have background in programming, and that's perfectly okay. This language reference does a really good job of showing you how to get started. Um, and so what we'll be doing is not overly complex, at least from my experience. I think this is pretty straightforward, right? It's only about 10 lines of code and it's all spelled out pretty well. Um, we will have a module where we go into more detail about how all these code constructs work together and how you might see them again in the future. But right now, we're just going to take it at face value and play with this all this example code and try to hack it, so to speak, to make it our own, really. Um, so yeah, again, the Arduino programming language is built on the C programming language. So if you have any experience with C, um, this will be pretty easy for you to pick up. There are a lot of good references for you to learn C on your own if you're interested. But now we'll just move on to electronic devices. So an electronic device conducts electricity, and here I've got a picture of Squirtle, right? Squirtle does not really conduct electricity, but Pikachu does. So that's pretty neat, right? Sorry. So different devices have different characteristics, and we usually describe these characteristics in terms of voltage and current. And we'll get into kind of one really important device characteristic that's described by Ohm's law for resistances in general. Um, but first, we talk about the conduction of electricity. So that means that electrons are moving. When something moves, there's a force involved. Electrons have negative charge, so they will flow from low to high. Um, and so we're just going to, without going too much into detail about the physics, talk about electricity. We'll save those, further discussions for your physics courses. But for now, we just take it that electrons are negative, they move from low to high, and then the direction of the current flow will be going opposite direction of electron flow. So that's called conventional current flow. Some people study circuits actually with electron flow, and there are different philosophies on which way we should go with that. But for now, we'll just be learning about conventional current flow, taking that current goes opposite the direction of electron flow. And so this way you can think of current flowing like gravity, right? So when I pick an object off the ground, I'm moving it up the gravitational potential of the Earth. And the moment I let go of that apple, it falls down, right? So it's much like current in that sense, going from high to low. So here's Ohm's law. Current flow is related to resistance and voltage. I is equal to V divided by R, where I is the current, V is voltage, and R is resistance. Current is measured in amps, voltage is measured in volts, resistance is measured in ohms. And so that's a capital omega symbol there, Greek letter. So resistors are electronic devices that add resistance, right? And again, resistance helps us slow down the current, right? And so they have some sort of nominal resistance, which tells you, hey, we've designed this resistor to be, 100 ohms or something. And then they're manufactured with some amount of tolerance. So if I have a 1% tolerance on a 100 ohm resistor, 1% of 100 is 1, so we can go from 99 ohms to 101 ohms, at least per the manufacturer specified tolerance. And again, yeah, so the tolerance defines kind of like the range of values which the actual resistance should be. So some devices need resistance for safe operation, right? Current flowing is a result of electrons moving, really. So things will get hot. These things are moving at the speed of light through, metal. Metal gets hot when there's friction, when there's something rubbing against it. So it's only natural that things will get hot is electrons are moving on it at the speed of light, near the speed of light at least. And so when things get hot, they break. So we need to slow down those electrons. Otherwise, much like in this picture or in this GIF or GIF, however you want to say it, right? The LED blinks for a second, but then instantly burns out. So again, diodes are electronic devices that usually need resistance. Here's a picture of different different resistances, right? And how bright the LED will be as a result of that resistance. Um, so that's one thing to keep in mind there. So here we have the forward current versus forward voltage plot for an LED. And you can see if we have tried to apply anything more than 2 volts to our LED, the current just shoots off, towards infinity. It's going real quick, right? So if I have a 5-volt power port on my Arduino and I try to apply 5 volts to that LED, it will quickly burn out, right? So here it says per the data sheet, and so here's the data sheet that we've got for just kind of like an example dummy LED here. So here we've got a list of absolute maximum ratings, and you can see here that the DC forward current is 30 milliamps, right? And so that's the maximum amount of DC current that we can put. There's also this list about peak forward current. So this is something, if we're pulsing the current really fast, it can handle this much current. But in a typical case, we're only applying DC, so this is a more appropriate metric to look at. So 30 milliamps. So maybe I ought to put that. So 30 milliamps DC current max. And so you can see quickly here that we shouldn't be applying more than about 1.9 volts. And even then, we should probably be applying less just to ensure that we're not hitting that absolute maximum and risking burning out the LED there. So the LEDs and resistors in our kit are through-hole devices, right? So they kind of look like these on the right here. They have really long terminals that you can stick through holes. Fortunately, the naming of that is very helpful. There are also surface mount devices like this one on the left here, which aren't really meant to be stuck through holes, but rather they sit on the surface of a printed circuit board. And you can actually see a lot of these on the Arduino itself, the Arduino development board itself. And the microcontroller especially is one surface mount device that has 100 pins, right? 100 of these little contacts, metal contacts that would stick onto the board. So jumping into the Arduino, the microcontroller, so we've got this Atmega 2560 microcontroller, kind of like in the center of the board here. And again, it has those 100 pins. It's a rather big part, and it acts kind of like the brain of the board itself, telling what all the pins to do. Well, actually, we'll be programming this microcontroller specifically. We'll be targeting that, um, telling it how to set up the pins, and then what kind of logical operations it should do once all those pins are set up. So here's the data sheet for that little Mega chip, and you can see here it's about 400 pages, a little over 400 pages, and it's got 100 pins. We'll be digging into this microcontroller a little bit more during the lab, but let me just get through all these slides here. So breadboards, they use the prototype circuits. If you were to, open up the bottom of the breadboard, this is kind of what it would look like. There are a bunch of metallic strips um, that are kind of like disconnected from each other. And this way, we can put through-hole devices into the breadboard to hook up circuits without having to solder them directly onto a printed circuit board and build circuits that way. On the topic of printed circuit boards, so these are usually meant to finalize a circuit, um, right? And so you will be designing one later in the course. But the main idea, right, is you solder them and solder all the components in place so that things don't move around and you have a fully working circuit. And so now we'll be talking a little bit about Tinkercad. So Tinkercad is a great simulation tool. Here I've got my Elmo. This is a 3D design, but you've also got options for circuit designs. And you would just click here, once you log in, and you can log in with your personal email or Cal Poly email, it doesn't really matter. But you hit create, you hit circuits, and then you'll be presented with this blank space with a bunch of components here on the right. And so we'll jump through this tutorial real quickly. So up at the top right, you'll be given some kind of random name. And if I left click that name, I can change it to something more meaningful. So just in this example, I changed it to LED example. So these are just the components that we'll be using for this tutorial. So we've got the Arduino, a breadboard, and an LED. And so, from here you can grab those components if you're following along. And then on the top right, there's a button for code. And so that'll be up here. And so that'll have interesting stuff when we actually have an Arduino here. So if I hit code, and typically what we want to do is left click this edit mode and go to text so that we can actually type out the code instead of playing with blocks. So this is just the default code. It'll turn on the onboard LED for 1 second and then turn it off for 1 second. And so you can watch that happen if you hit start simulation up here. And so here I've got it running and you can see my onboard LED is going on and off there. Really cool. Um, so this is just me taking a look at the language reference. And so you notice that in the code, they're using this all uppercase thing that doesn't really seem to be defined anywhere in the code itself. So this is actually a feature of the Arduino language itself. And so if we actually go into the docs, we can see a list of variables that are predefined. And so these capital ones, these are called macros. And so basically what happens is when you compile the code, it'll replace these macros with whatever they're defined as. So in this case, we click on LED built-in and we can see it should just be defined as 13. Um, so that's just something to keep in mind, why kind of like the reasoning behind the usage of these macros. If I were to actually just replace all of these with 13, it would have the same effect of turning this LED on and off. And so we can verify that here, right? And so that's going on and off. And just to, as another sanity check, if I were to change all of these to 12, so that onboard LED should no longer cycle on and off, because now it's this digital pin that's turning high for 1 second and then low for 1 second. So now we're going to jump into a little bit about the theory of LEDs. So LEDs have an anode and a cathode. So here you can see this kinked leg is the anode, the straight leg is the cathode, just on this Tinkercad. And so when we have more voltage, right, a higher voltage on the anode than the cathode, then current will flow pretty easily through the LED and it'll emit light. Otherwise, it'll block current and the LED won't turn on. And so here we can just see an example of that. If I hook up ground, right, which is 0 volts to the anode, 5 volts to the cathode, nothing happens. But if I reverse that, then we can see a lot of current going through the LED. And actually, in this case, the LED will probably explode. Not explode, but burn out, rather. So here we put in a 220 ohm resistor, and so in Tinkercad, right, if you go to the tool to the components here, there's a resistor, and you can change the resistance, just by left clicking it, and this informational window pops up, and you can change the amount, from kilo ohms, which is a factor of 1,000, to just ohms. Right? If I were to change it to 220 ohms using kilo ohms, that would be 0.22 kilo ohms, right? Because if I move that over one, two, three places, I get 220 ohms. So we'll get into measuring next week, but this is just to give you a sense of kind of what happens when we add this current limiting resistor. You can see the 5 volts is divided amongst the LED and the resistor, which is really good because, we looked at that forward voltage versus current um, chart from earlier for a specific LED, and we saw that we don't really want to be putting it, too far above 1.7-ish volts. And so in this case, it drops down to 2 volts from what we had before, which was 5 volts, which is certainly too high. This is still a little high, but I think it doesn't show that error that we had seen before here with this thing exploding. Um, so that's good. That should be sufficient. So in the top right, we can toggle between the circuit and schematic view. So schematics are really helpful for seeing what the circuit actually looks like. And so in this case, I don't have anything connected up, but this is what my schematic looks like in my surprising loppy uh, circuit here. It's really great. But so here's the kind of physical representation of the circuit. Here's the schematic for, this tutorial example at least. Um, and now let's talk about breadboards. So breadboards, as I mentioned before, are used to prototype circuits, and so we can connect things into these sockets, right? Especially these through-hole components are pretty easy to connect up into the sockets. And one thing to keep in mind is how things are connected internally. And so whenever you hover over a column or a row, you can actually see what sockets are connected underneath, right inside of the breadboard. And so this way, it gives you an easy way of understanding how to go about building your circuit. So here you usually want to start off with the schematic, right? We can't just start putting in components without knowing what it is we're building. So we start off with the schematic, and in this case, I like to start off with power. So I have 5 volts coming in off of the Arduino, so I'm going to start with that. I'm going to take some wire, I'm going to connect that 5 volts into the positive rail of my breadboard. And so this positive rail is typically used for power. So that's good. And then I'm going to take that power and I'm going to jump it into the breadboard. I'll connect it to the anode of the LED, which I've got shown in my schematic here. I'm going to take the cathode of the LED and I'm going to connect a resistor. Right, and so I've got the cathode to the resistor, and then the other end of that resistor is now going back to the Arduino ground, which I've broken out with a wire to the breadboard, and I connect it to the resistor right in the bottom right here. And so that way we've created the circuit completely, and now we can get to simulating it. So um, right at the moment that I start the simulation, this LED will turn on. Um, And here I just want to make a note that you don't always need the power rail. So for example, if we're using kind of a digital pin to control, an LED turning on and off, in this case, we don't need to use the power rail. We can just connect directly to the LED anode. And so this makes a circuit from the anode, right, the cathode to the resistor, other end of the resistor back to ground. And so here I've written some code to turn pin 7, digital pin 7, which I've got connected here, high and low. And so what that'll do is it'll go to 5 volts at this node, right, for 1 second, and then it'll go to 0 volts for 1 second. And so that's why the LED is turning on and off there. And so that concludes kind of this demonstration, right, and this overview of the first module. Thanks for tuning in. Feel free to let me know if you have any questions, but otherwise, I'll see you guys in the lab. Thanks.